Okay, we're starting off your spring break in the best way possible with a homework review. So this is for Chapter 5, Homework B, the second of two Chapter 5 assignments, and it was all about stoichiometry, as you guys saw. So the average this week was 9.27 out of 12, basically the same as previous years. So, these types of problems, they're not necessarily difficult, but there are sometimes multiple steps, and obviously, as you know, missing just one of those steps even a little bit can cause you to get the whole problem wrong. So it's important to be very detail oriented and to really know that when you're doing these problems, what each step means and how to sort of rationalize everything you're doing. You can become a little bit robotic with these problems and kind of just learn and mimic the steps for doing them, but at the same time it's important to understand what you're doing, so if you ever see a variation you'll be able to handle that appropriately. So let's get into the problems. So there were some problems on this assignment that dealt with balancing chemical equations, and we did pretty well on that for the most part. But here's one that I want to cover that's a little bit more conceptual in nature. So we have a sort of a chemical reaction represented in a very generic way. It says specific chemical reaction, but it's actually not very specific because it doesn't have real numbers or real chemical species represented. It's just A plus B goes to C plus D with some coefficients. And we want to know, so the capital letters are the compounds or elements that are in the reaction, and the small letters are the coefficients. So what we want to ask here is how many possible values are there for the quantity C over D? That'd be the ratio of the two coefficients on the product side. So again, writing out this equation, we obviously can't really balance it because we don't know what A, B, C, and D are. But let's think about how we could balance this if this was a real chemical equation. Now, conventionally, we balance things with the smallest whole numbers possible, right? That's kind of the way that we do it in most problems when we ask you to do it. But you should recognize that there are infinite numbers of ways to actually balance the equation. So, we could do smallest whole numbers, but we could do fractions that are related to those whole numbers, or we could double the coefficients and so on. So as an example, sometimes it's easier to just put real numbers on this. Let's assume that the correct way to balance this was just to put A plus 2B goes to 3C plus 4D. Alright, so let's say that that's the correct balancing. We have no idea if that's right or not, but let's just assume it is. 1, 2, 3, 4 for the four coefficients. So that's one way to balance the equation, but we should recognize that even though this is the most conventional way with small whole number of coefficients, we could do fractions. That would work. So if we took all these coefficients and divided them by 2, we could have half A plus B goes to 3 halves C plus 2D. So we could balance it this way where all the coefficients are half, or we could double all the coefficients and so the possibilities are endless. But remember, whatever we do to one coefficient, we have to do to all of them. But as long as we multiply each coefficient by the same factor, the reaction will still be balanced. Not necessarily in the most conventional way, but it works out either way. But what we're asking here is not how many possible coefficients are there for all the equations, or all the species. It's asking for what is the number of values for the ratio C over D. Now what you should realize is that the ratio of two coefficients will always be the same, because if we change one coefficient by a certain factor, we have to change the other one by the same factor. So in its sort of standard form, C over D here is 4 over 3. I didn't pick the easiest numbers, but it's 4/3. Here we would do C over D for the second one is 2 divided by 3 halves, which simplifies to 4 over 3. Or in this bottom one here, C over D is 8 over 6, which is also 4 over 3. So when you're talking about a ratio of two coefficients, those will stay the same no matter how you balance the equation. So as long as the equation is balanced, you would do the same thing to all the coefficients, multiply or divide by the same factor to keep it balanced, and in doing so, the ratios of any two coefficients will have to remain the same. So there's only one possible value for that ratio, C over D, or any ratio of two coefficients, A over B, A over C, A over D, and so on. And that's how stoichiometry works, because remember, stoichiometry works on the basis of mole ratios. And no matter how you balance the equation, as long as it is balanced, you'll be able to get the correct answer in a stoichiometry problem, because the mole ratios, which are the key parameters you use in stoichiometry, will stay the same. So that one asks you to think a little bit, and it's not actually balance the equation, but think about in sort of conceptual terms about that topic. Now the rest of the problems that I'll do today all deal with stoichiometry. Most of them are numerical problems. And when we're doing a stoichiometry problem, the first thing we always have to do is produce a balanced equation. There's no shortcut around that. And then from there, we need to figure out what the limiting reactant is in the situations where that matters. So those are the things we're going to think about. Now the first few that I'll do, we actually don't need to worry about limiting reactant, because as I'll show you, in all of these, we're either starting with the amount of product and calculating moles of a reactant, in which case you assume that you have sufficient amounts of both reactants, or we're giving you the amounts for one reactant and sort of telling you that the other one is excess. So in these first few, we don't have to worry about limiting reactant. We always want to have that in the back of your mind. So this one here, we're talking about ethyl alcohol combustion. Now part of the trick of this one is producing the correct balanced equation. We haven't talked a lot about combustion in this class, but we did mention it a few times in a few contexts. And so combustion, what we're doing is we're taking an organic compound, usually a hydrocarbon or a hydrocarbon with some oxygen in it, possibly like this one here, an alcohol, and reacting it with O2. And then the products for any combustion reaction are always the same, CO2 and water. Now, whether we got this exact equation right or not, we'll have to put the coefficients in here to finish it. What we should recognize, and we should already know by now, is that when you burn something, when you do a combustion, all of the carbon in the reactant you're burning ends up in CO2. So the important thing is the ratio between what you're reacting and the CO2 in this problem, or sorry, water in this case, because we're looking for grams of water, and mess that up. But you form CO2 in water, so all the hydrogen goes into water, all the carbon goes into CO2, so getting those ratios is the most important. So if we were to balance this out, C2H5OH with excess O2, we have 2 carbons on the reactant side, so we need 2 CO2s. And then this reactant here, C2H5OH, total of 6 hydrogen atoms, so we need to have a coefficient of 3 in front of H2O. And for this problem, getting those coefficients correct is the important part, because, again, O2 is in excess, so we're not going to really use it in any of the calculations. But if we want to finish balancing this, we would have 4 plus 3 is 7 oxygens, plus 1 here from the reactants. You can't forget about that one, so it would be 3 O2. Should balance it out. So there should be 7 O2s on both sides. So that's the correct way to balance it, but like I said, we don't really need the coefficient for O2 for this particular problem, because we're just dealing with the ethanol, C2H5OH, and the water. But with that in hand, we can now proceed with the problem. So here we're giving you moles of the reactant, with the other one being excess. We want to know how many grams of product are formed, so from there we can just set up what we're looking for. So we're looking for grams of water, and we're starting with moles of C2H5OH. So we write out what we're starting with. In the stoichiometry problem, the first thing you typically want to do is convert to moles, but here we're already giving it to you in moles, so we don't have to do an extra step, and we can use the mole ratios directly. So we want to get into water, so we want moles of water on the top, and we want moles of this reactant ethanol on the bottom. And if we look at the coefficients, we have a coefficient of 3 in front of water and a coefficient of 1 in front of ethanol, so it's going to be a 3-to-1 mole ratio. We're not going to stop there though, because we're looking for grams of water, so now we have to multiply by the molar mass. So I'm not going to calculate molar mass in detail, but for water it's 18.02. We learned that we covered that in last assignment, how to calculate molar mass, so we're not going to go through it here, but it's 18.02 grams per mole for water. And so those are the 3 things you just need to multiply together. So what I got was 435. I think this one may have been, I don't know if this is multiple choice or numerical. You might have variable inputs here. So you could have gotten different numbers, but same series of steps. Alright, so assuming I did that correct, we should get 435 grams of water. And that's a mole to mass stoichiometry problem. So if you want to classify it, you're starting with moles and calculating a mass. This would be called mole to mass, but you don't have to always do that classification, because the series of steps is just going to be whatever it takes to get from what you're given to what you're looking for. So this problem is very similar, but this time we're just going mass to moles. So we're giving you the mass of one chemical species in the reaction and asking you to find the moles of the other. So here it's N2 and H2 to form NH3, a very important reaction industrially. It's involved in making all the fertilizer that we use in the world. So it's a pretty simple reaction to balance. N2 plus H2 NH3. If you want to balance it with fractions initially, so if we set NH3 to 1, we need to have 1/2 N2, and then we have 3 H2, 3 hydrogens, so we're going to have 3/2 H2. So that'll be balanced, but I like to work with whole numbers, so we're going to double everything here and just write it as N2 plus 3H2 going to 2NH3. So everything is balanced in this way, and we're using whole numbers, which makes it a little bit easier to deal with. So again, we start with a balanced equation. We have to figure out if we need to worry about limiting reactant here, but in this problem, we again don't have to worry about that because we're figuring out how much reactant we need to produce this much product. So we're giving you an amount of product and asking you to calculate one of the reactants. And furthermore, it says if sufficient N2 is present. So that means N2, when we say it's sufficient, it's either the exact right amount or it's in excess. So again, we don't have to worry about the amount of N2. It's not given to us, and we're being told that there's enough of it there. So all we have to do here is just calculate moles of H2 that are needed to produce this much of the NH3 product. So we write out what we're looking for, which is moles of H2, and we write out what we're given, which is 58.4 grams of NH3. As I said in the last problem, the first thing you want to do in stoichiometry is convert to moles. We don't have that now, so we're going to use the molar mass of NH3 to convert grams into moles. So we're going to divide by that number, 17.03 for NH3, so that grams cancel, and now we're in moles. Once we're in moles of one reactant or product, we can calculate the moles of anything else using mole ratios. So we're looking for moles of H2 here. So we want H2 in the numerator, and we want NH3 in the denominator so that it cancels out. And then for those, we just use the coefficients, 3 for H2, 2 for NH3. And that's where we're going to stop, because again, we're looking here for moles of H2. That's what we've gotten to, so we don't have to do any last steps. We're just going to stop there. So this was a mass to mole, where we're starting with the mass and calculating moles. So same number of steps, just go in a different order. And what I got for this one was 5.14. Hope I didn't mess up anything. And the calculations I'm going to do kind of quickly here. But I got 5.14 moles of H2. And again, I think this was a numerical problem where you could have had different numbers but same set of steps. Alright, so that's another one where we don't have to worry about limiting reactant. And then finally, one more where we don't have to worry about limiting reactant is another combustion one. So we're combusting 10.6 grams of C4H10, which is butane, and we want to know how many grams of CO2 will form. Now, as we said, we should be able to write out the balanced equations for combustions now, and especially realize that when you combust something, the two products you get are always carbon dioxide and water. In a typical combustion reaction problem, O2 is going to be in excess. You're burning the substance in air, typically, for a combustion. So you have O2 all around. You're never going to run out of oxygen. And so what you're mostly concerned with are ratios involving the compound you're burning, in this case C4H10, and whatever products are forming, CO2 or water or both. So we have to get those ratios correct. So C4H10 has 4 carbons, so it's going to form 4 CO2s, and then 10 hydrogens, so it'll form 5 water. So that's the ratio that's important, 1 to 4 to 5. If we want to completely balance this, we need the O2 as well, so it's going to be 8 plus 5 is 13. So for O2, it would be 13 over 2 to have 13 oxygens on both sides. So if we wanted to get full numbers for this, we'd have to double everything, but we can leave it like this also, especially since we don't need to worry about O2 in this problem, which is in excess. So what we're going to do here, we'll just leave this in this form, and then we're going to go and calculate what we're looking for. So this is now a mass-to-mass problem because we're giving you the mass of a reactant and asking you to calculate the mass of a product. So we would classify that as mass-to-mass, but the series of steps we're going to just, again, follow the same approach. Write out what we're looking for, grams of CO2. Write out what we're starting with, which is grams of C4H10. First thing we do in stoichiometry is convert to moles. So if we're given a mass, we just use molar mass to convert to moles. That should be 58 plus something. Let me get that number exactly right. Alright, so I got 58.12 for being fairly exact with that. So it's 58.12 grams per mole, so we divide by that to get into moles of C4H10. Once we're in moles of any reactant or product, we can convert to moles of any other reactant or product using mole ratios. So what we're looking for in this problem is CO2, so we're going to use that mole ratio with CO2 on the top, C4H10 on the bottom so that it cancels out. And the coefficients 4 for CO2, 1 for C4H10. Again, we didn't have to balance the whole equation to realize that because all of the carbon goes to CO2 in a combustion reaction. So if you have 4 carbons in your reactant that you're burning, you're going to form 4 moles of CO2 as the product. So that's moles of CO2, but in this problem we don't stop here because we're looking for grams of CO2. So now we have to use its molar mass, which is 44.02, to convert from moles back into grams. So this is again a mass-to-mass problem. We're starting with a mass, ending with a mass, so we have to go use molar masses in both places. So once we do that, then we should be able to get the right answer. So let me calculate it out real quick. And it should be 32.1. grams of CO2, again assuming I didn't screw up my math, so definitely double check me on that. But those are the right series of steps, mass to mass. So we start with mass of reactant and convert into a mass of product using this series of steps. And again, this was another problem where we didn't have to worry about limiting reactant because we're only telling you the amount of one reactant. So in any problem where we only give you the amount for one reactant, you really have no choice but to assume that any other reactants present are in excess. So we don't have to worry about limiting reactant in that case. But the rest of the problems deal with limiting reactants, so we're going to have to talk about that concept. And remember, the idea with limiting reactant is when you're mixing together two quantities of substances that are going to react with each other, you know, unless they're in the exact right mole ratio, one of those quantities is going to limit how much product is formed. So the limiting reactant is going to react completely 100% form the product, and the other one is going to be some left over. So the first question here deals with sort of the conceptual basis of limiting reactant, knowing which one is limiting reactant and why, and you know which one of these is true. So let's go through and look at this problem here. So we have 3A plus B goes to C plus D. So here again, sort of generic chemical compounds in this reaction, but this time we have real coefficients. 3 for A, 1 for all the rest. And we're saying we react 2 moles of A with 1 mole of B. So dead giveaway, we have amounts for both reactants A and B, so we know that this is a limiting reactant problem. And we want to know which of the following is true, and all the answer choices deal with what the limiting reactant is. So I think the most straightforward way to approach this problem, instead of trying to read all 5 answer choices and debate them, is just figure out what the limiting reactant is, because whatever answer we pick requires us to know a limiting reactant. So remember that the way that we find limiting reactant is with what's called stoichiometric ratio. So we're going to calculate the stoichiometric ratio R for each of the 2 reactants. So for A, remember the stoichiometric ratio, this is the way that I like to do it to find limiting reactant. There's other ways of going about this, but I like this approach because it's the most straightforward in my opinion. You take the moles of that substance and divide it by the coefficient in the balance equation. So for A, we are told that we're reacting 2 moles of A, so we're going to put 2 in the numerator, and then we divide that by the coefficient. The coefficient in the balance equation is 3, so 2 over 3 is the ratio for A. And then for B, we have to do the same thing for stoichiometric ratio. So the moles of B that are present, which is 1, we're told here they have 1 mole of B, and we divide that by the coefficient for B, which is also 1. There's no coefficient in the equation, which means it's assumed to be 1. So the stoichiometric ratio for B is 1. So comparing those two numbers, 2 over 3 and 1, the smaller of those two indicates the limiting reactant. So 2 over 3 is smaller than 1, so that means A is our limiting reactant. So whatever answer choice we pick needs to identify A as the limiting reactant, so we can get rid of C, D, and E, which say that either B is limiting reactant or neither is limiting. But then for A and B, we have to figure out why it is. So A is limiting reactant because of its higher molar mass. Well, we didn't tell you anything about the molar mass in this problem, and moreover, that doesn't directly factor into how we determine the limiting reactant. So that one's going to be false as well. That leaves B is the only one that's left. A is the limiting reactant because you need 3 moles of A and have 2, and that's exactly right. We have 1 mole of B present. From the balanced equation, 1 mole of B reacts with 3 moles of A, so we would need 3 moles of A, but in reality only 2 are present, so that's the correct answer there. Alright, so that's going to be the correct answer choice. It identifies the limiting reactant correctly, and it gives us the right reason why. Alright, so from there we're going to have just a couple of problems here that deal with using the concept of limiting reactant to solve a stoichiometry problem. Just give me 1 second. I gotta pause this for a second again. Alright, so we're gonna go through and do some limiting reactant problems now where we're going to use that concept, that idea of limiting reactant, to actually solve a numerical question. And as I said, the key way to recognize whether you have to be concerned with limiting reactant is if we give you amounts for 2 or more of the reactants. So here we have calcium reacting with sulfur, forming calcium sulfide. And we want to know the theoretical yield of calcium sulfide that can be prepared from 3.34 grams of calcium and 3.75 grams of sulfur. Enter the answer with 2 decimal places. So this is a numerical question. Your numbers would have been possibly different, but same series of steps no matter what. So we have to write the balanced equation. The simplest way to write this is calcium plus sulfur forming calcium sulfide. Just 1-to-1 reaction, so not too much going on there. Now, technically speaking, as we'll learn later in the course, sulfur is actually S8 in its natural form. So we should, being chemically correct, we should balance it in this way. So we'll have an 8 there and an 8 there. It actually turns out it doesn't matter how you balance it. You'll get the same answer either way. And that's because, you increase the molecular weight of sulfur by a factor of 8, but then its relative coefficient is decreased by a factor of 8. So again, in terms of all those ratios that are important, nothing changes. So I'll use this top form here because it's simpler and because this is probably the way that you guys balance it, because at this point we haven't really learned that sulfur exists as S8 naturally. So we'll just use that one and we don't have to worry about this for now. But now what we have to go through is we have amounts of both reactants, calcium and sulfur, so we need to figure out what the limiting reactant is. So to do that, we're going to follow the series of steps that I outlined in the previous problem, which is to find the moles of each reactant first and then divide by the coefficient. So the moles of calcium, we have 3.34 grams. And then we're going to divide by the atomic mass since it's an element. So 1 mole of calcium has a mass of 40.08 grams. That's straight off the periodic table. So the moles of calcium are going to be 0.0833. And the stoichiometric ratio for calcium is just going to be that number divided by its coefficient. The coefficients in both of these cases are 1, so it's just going to be that number itself. And then for sulfur, we have 3.75 grams. And we're going to use its atomic mass to get the number of moles. So again, we can just balance it with S sulfur. We don't have to use S8 necessarily, but if you'd use S8, you'd still, again, come to the same conclusion. So when we calculate moles of sulfur by dividing by its atomic mass, we get a slightly larger number. So let me see what that number is here in a second. We get 0.117. And the stoichiometric ratio for sulfur is that number, again, divided by 1, so it's just that number. So this stoichiometric ratio for calcium is smaller, In this case, we could just use the number of moles because the coefficients are 1, but that's not generally true. We have to remember to divide by the coefficient and get R, which is smaller for calcium. So whatever calculation we're going to do is going to start with calcium. So what we're looking for here is the theoretical yield in grams of calcium sulfide. So we're looking for the grams of calcium sulfide that can form. And we're going to start with limiting reactant. So we already calculated moles of calcium, so let's just start with that number because it saves us a step. But you could have also started back at the beginning with mass of calcium. So we have 0.0833 moles of calcium. And then from the balanced equation, it's a 1-to-1-to-1 reaction. So 1 mole of our product forms for every 1 mole of calcium that reacts. So that's moles of calcium sulfide, but we need grams, so we have to multiply by its molar mass, which is just the sum of calcium and sulfur, which is 72.15. So 72.15 grams of calcium sulfide in 1 mole allows us to convert into the grams of product form. So I got 6.01. They want 2 decimal places, so we write it as 6.01 grams of calcium sulfide. Of course, just entering the number into Blackboard. We don't want to include units or labels, but that's the number, 6.01. All right, so that's how we would do a typical limiting reactant problem. You have to figure out moles of each reactant, divide by the coefficient. Once you identify a limiting reactant, everything starts from there. So this one is a very simple one, but now it asks us to calculate percent yield. So here we're making nitric oxide from the oxidation of NH3. And actually this one doesn't require us to figure out limiting reactant. I was mistaken when I first looked at this one, because here we're reacting 9.3 grams of one reactant, NH3, and we're telling you how much product is forming. So again, we're not telling you the amount of O2. So since we don't give you the amount for that reactant, we have to assume that it's in excess. So in this problem, we don't have to worry about limiting reactant again. But what we're doing here is a little bit different because we're calculating the percent yield of NO. So here in percent yield, we saw this on some of the homework problems as well. Percent yield is when you run a reaction, you measure how much product is formed, and you compare that to the theoretical yield, how much product could be formed in a perfect situation. So what we're going to do is we're going to take the actual yield divided by the theoretical yield, and then multiply by 100 to make it a percent. So in these types of problems, actual yield is typically given to you, and that's this number here. 12.0 grams of NO is how much we're getting. Oh, looks like I left a subscript out. There should be subscript 3 there. That's how much NO we're getting. We want to know what the percent yield is, so we have to calculate theoretical yield. So in most problems like this, we give you the actual yield, and then you have to calculate the theoretical yield on the way to getting percent yield. So when we calculate the theoretical yield, that's just the mass of the product, in this case NO, the product that we measured, that can theoretically form from the limiting reactant. So NH3 is a limiting reactant. It's the only one that we have the amount of. So we're going to just do a mass-to-mass stoichiometry problem to figure out how much NO could form from this. So 9.3 grams of NH3. We convert to moles first in pretty much any stoichiometry problem. So we use the molar mass of NH3, which is 17.03 grams per mole. Divide by that to get moles of NH3. Once we have moles, we can get moles of product by using stoichiometric ratios. So 4 moles of NO form for every 4 moles of NH3 that react. They both have coefficients of 4. So that cancels out moles of NH3, and then to get the theoretical mass of NO in grams, we have to multiply by its molar mass, which is 30.01. I think my tablet froze again. Darn it. Alright, back from the unplanned break after my tablet flaked out again. Of course, I was close to being done, and that's when it had to happen. So again, apologies for that, for the sort of halted, interrupted presentation of the problem. So what we have been doing is, again, we want to calculate percent yield So we're looking for actual yield and theoretical yield. Actual yield is given to us. So now we're calculating the actual yield using stoichiometry. So we start with grams of our reactant NH3, convert to moles, use mole ratios, and then finally what I was about to do was use the atomic mass, molar mass of NO to convert into grams of NO. So that's how much NO can possibly form. So when we multiply that out, what we get is 16.4 grams. So that's our theoretical yield of NO. That's how much NO can potentially form, and now we're going to put that back up here to calculate percent yield. So actual yield is given as 12.0 grams. That's how much we're told is forming. Theoretical yield is a number that's bigger than that. It should be 16.4 grams is how much NO could potentially form, and then multiply that by 100. So 12 divided by 16.4, and then that's going to be 73.2%. Alright, and again, I don't remember if this was multiple choice or numerical, but either way, those are the series of steps you would take. So we get 73.2% for our percent yield in this problem following those steps. So another one where we didn't have to worry about limiting reactant because, again, the amount of O2 was not explicitly stated, so we assume that it's in excess. Alright, last problem here is another limiting reactant problem, but just presented in a little bit different way. So there were a few in this homework assignment that involved these sort of pictures of chemical reactions. I want to make sure that we understand how to approach these. So what we have here is a mixture of A2, which is in green, and B2, which would be blue then, and they're reacting to form AB3. So we're not showing the product, but this is basically a mixture of our reactants that are present. So it's A2 and B2 forming AB3. So we have to make sure that we balance it correctly. And we need to know which is a limiting reactant and how many AB3 molecules can form. So here we're dealing with individual molecules instead of moles, but remember that those two quantities are just related by Avogadro's number. So whatever concepts we have that involve moles, again using stoichiometric ratios to find the limiting reactant, we can also use that in terms of individual molecules as well. And so for this problem here, we have A2 and B2 forming AB3, so we need to balance that out correctly. So we need a 2 there and a 3 there to balance that. That's a lot like the equation we did earlier with N2 and H2. Now we're asking which is the limiting reactant and how many AB3 molecules can form. So to find limiting reactant, we need to find the stoichiometric ratio for each of them. So for A2, we're going to find how many molecules of A2 there are now, which again is related to how many moles there are, and we're going to divide that by the coefficient. So A2 is in green, so we have 1, 2, 3, 4, 5, 6 green molecules, and the coefficient for A2 in the balance equation is 1, so the stoichiometric ratio for A2 is 6 in the molecular scale. And then for B2, which is in blue, we count how many molecules there are, 1, 2, 3, and the coefficient for B2 is also 3, so that stoichiometric ratio is 1. So clearly B2 has the smaller ratio, so this is going to be our limiting reactant. So that was part of the question. I think it was a multiple choice. I'm not giving you all the answer choices, but B2 is a limiting reactant. So that's part of our answer. And then it also wants to know how many AB3 molecules can form. So for this one here, again, we're doing it in terms of individual molecules, but the concept is the same as if it was in moles. So the molecules of AB3 that can form, we start with the number of molecules of our limiting reactant we have. So B2 is limiting reactant, and as we said, there's 3 molecules present, 3 of those blue molecules. And then using the stoichiometric coefficients, we can figure out how many molecules of AB3 would form, because these coefficients can be interpreted in terms of moles or in terms of individual molecules. So we have a coefficient of 2 in front of AB3, so 2 molecules of AB3 are going to form for every 3 molecules of B2 that react. And so that tells us then that we're going to form 2 molecules of AB3. Alright, so B2 is limiting reactant, and we're going to form 2 molecules of AB3. So those are the 2 parts of our answer. Alright, so in this case, it may have been more, not as difficult as it looked, because we're just giving you the picture where you just have to count how many molecules there are and then use those in the same way to find stoichiometric ratios and then do stoichiometry using that information. Alright, so that takes us to the end of the review. Again, sorry for the interruption caused by my tablet going on spring break already. So if that caused any problems, let me know on that previous problem if you had any questions that aren't clear because of the interruption that I had. But I think everything was covered okay, and if you have any other things you want to talk about with related to this homework assignment, please get in touch with me. We'll just have one more assignment after spring break that'll be before the second exam. That assignment is already opened, but it's not due until after spring break, so that will be when your next video comes. Alright, so thank you for tuning in, and I will see you guys in class after you all hopefully have an enjoyable spring break.